So the next graph here is what? Is velocity time what? Time graph. Let me put motion here. Velocity what? Time what? Time graph. So the next one is velocity time graph. Velo what? Time graph. So in velocity time graph, it's a graph of what? Velocity against what? Against time. Graph of velocity against what? Time. Have it in this. So this side will be what? Velocity in meter per seconds. This place will be what? Horizontal axis will be this. And so if you now plot the graph, you have a straight line like this. And then you now look at what? The gradient of the curve. Look at the gradient of the curve. Find the gradient of the curve. We have to change the t here. We have to change the d here. So the gradient here, with the slope, it will be changing what? Sorry, changing v over what? Changing t. And this symbol, which is the change in velocity over time, is what? Is as a what? Acceleration. So this graph is the what? Acceleration graph. And it's a straight line graph. You now call it what? Uniform. As a what? Acceleration graph. But in case of we have velocity against what? Time. Against time, this is what? Velocity in meter per seconds, time in seconds. And by drawing the graph, the curve is going like this. You can see that what is also what? Not what? Straight. And to know the what? The slope for this curve, you can pick a what? A point here, draw a what? A tangential what? Line that will touch the what? The curve. Then from here like this, you can have the change in v, change the t. You now have what? Slope or gradient of the curve with what? Acceleration. Since the graph is not straight, what are we going to call the graph? Non what? Non-uniform as a what? Acceleration graph. The next one is what? If you have another what? Vertical line against what? Vertical line against this. And if you look at the graph here, this like this, and we have a velocity in meter per seconds and time. This, and you are having, look at this one. This one is what? is slightly upward. But if your graph instead of slightly upward is slightly what? Slight. It's coming from here and slide down like this. Coming from the up here and what? Slide down. And the graph is still a what? A straight what? A straight line curve. So by plotting the graph of this, or by finding the slope of this curve, slope here, for this curve, the change in V against change in T, here, the slope will give us what? Negative value of what? Acceleration. And whenever the what? The acceleration, you have negative value of acceleration, or the velocity here is what? Is decreased. Here, the rate of velocity here is what? Is increased from 0 upward. But here, the rate of velocity is what? Decreased from upward to what? To the 0. And if you have a graph that is what? The rate of velocity is what? Is decreased. So the graph, the nature of the graph is what we call what? Uniform. Is uniform because it's straight. Deceleration. Acceleration graph or uniform retardation. Whenever the acceleration is what? Is negative, we call it what? Deceleration or retardation. When the rate of change of what? Velocity is decreased. When is what? The rate of change of velocity is what? Is increased, we have acceleration. The next graph now is what? Graph of have a what? A vertical axis like this, and I will plot it against what? And we plot it against time. Velocity against time. And if you now look at the what? The curve. The graph is parallel to time what? Time axis. Whenever the graph like this, like this now, and the graph is what? Parallel to what? Time what? Time axis. And this is what you observe that what? The time change, but velocity at this particular point here is not what? Is nothing, it's constant. So for this kind of graph, velocity is what? Is constant. When velocity is constant, then acceleration for this graph is what? Is 0. Because acceleration is always what? The, what I call it, is the change in what? In velocity with time. Here, velocity is what is constant, it does not what? Is not change. So V is the graph of what? As velocity is constant and A is what? Is 0. So now call this one what? Graph of what? Of constant velocity. So what? Constant what? Velocity graph. For this kind of graph, what happened there? The what? The acceleration is what? Is 0. So the next thing now here we have is what? Let us combine the one. Let us combine these three graphs together. 1, 2, and 3. See, by combining the three graphs together, hmm, what? Then let's combine. Let me call this one what? 1. This is 2, Abi. This will be what? 3. This will be what? 4. So what? Combine, let's combine graph 1, 3, and 4. By combining the 4 graphs together, 3 graphs together in this sketch, we have and this is what? Time in seconds. This place will be what? Velocity in meter per seconds. So by combining the 3 graphs together, we have what? We have a slight line like this, get to this point. We have another curve like this, get to this point. This curve slides down. So curve slide what? Slide down. We now have the point here for the curve here. Let me call it what? T1. This place, let me call it what? T2. The point where the curve end here, let me call it what? T3. This is it. Time in seconds. And the point of here, call it what? T0. And I can also then the point here, call it what? Velocity. Or if I like to, I can also call this place what? A, A, B, C, let me say A, B, B. This point is what? C, D. Here we have E. This place, let's call it what? F. We can observe that what? We combine the what? This graph, this one, and this together. From there now, can I say that what? This is what? This graph is as a what? Acceleration. This one is what? Deceleration, constant velocity. And I say what? This is as a what? Acceleration. Where this one is what? Constant what? Velocity is what? Constant. So this place will be what? Deceleration. So in this graph now, you can observe anything you have inside here is what? Acceleration. And from this graph, anything you have here is what? Deceleration. So from this graph now, we can deduct 3 things here. Can deduct what? 3 what? 3 things. I say what? Deduction from the what? From the graph. Deduction from the what? From the graph. The deduction from the graph below or graph above, put above. Number one, the first thing that you can deduct from the graph is acceleration. So if you're asked to find the acceleration from this graph, acceleration what? A. It will be everything you have here, the top here, the value you have here over what? The time you have here. The acceleration will be what? The value you have here for your velocity over what? Over time taken at this point. It will now be what? V over what? Over T1. That should be the what? Acceleration of the what? Of the graph. The second thing that you can ask you to what? To determine from the graph, how to find deceleration. Deceleration is when acceleration is what? Is negative. So it will be what? The value you have here, which is your V. V over what? The final value you have here minus the initial value, which is what? T3 minus T2. That's what? Deceleration. The last thing they can ask you to find here is what? Total distance cover. What is total distance cover? Is the area of the what? Of the shape. And it's not must that for the velocity time graph that we have what? A trapezium. The shape of velocity time graph is not trapezium, it's not constant. It depends on the traveling of the what? Of the particle. So I'll just give this as a case of study. So here now, the total distance covered for the body to move from A to B to D to what? To F. So it will be the what? The total what? Distance what? Covered. So the total distance covered here is what? It will be equal, the same thing as what? Area of the what? Of the shape is equal to the what? Area of the shape. And if you look at this place now, the area of this shape is what? Trapezium. Like I said, here we have what? Area of this place is what? Trapezium. That's what? Total distance cover here. Total distance cover will be equal to the what? Area of trapezium. So the area of trapezium here is what? Half of A plus E, this plus this, then times what? Height. Here, half of what? Total distance here, AF. AF plus this distance, BD, the what? The height you have here. A what? AB. So this is what? Area of what? Of trapezium. If you apply this formula, for trapezoid, you get the what? Total distance what? Covered. But in a easiest way, if you can see this structure very well, you all at what? It comprises of three shape. Yeah. All of what? Of three what? Shape. What and what shape? This place is a what? A triangle. This place is a rectangle. B. This C is what? Triangle. So, you, or another method of finding total distance cover. You can say what? Total what? Distance covered is equal to what? Area of what? Triangle A plus area of rectangle B plus area of triangle C. If you can learn how to use this formula, in fact, it will be best to calculate the what? Total distance covered. So TDC of this shape, what is the area of triangle A? Please look at it now. This is triangle A. It look like this. This is triangle A. It look like this. Plus rectangle. It look like this. Plus triangle. It look like this. So this one, we call it what? A, B, C. So what is the total distance covered? This one is half base times what? Height plus length times what? Breadth plus half base times what? Height. So if we look at what? The base of this one is this, height is this, length times breadth. This times what? This one is, so this is what? The best formula to use to calculate what? The velocity time what? Time graph. We will solve question on it. We will solve question on how to use what to calculate the velocity time what? Time graph. So let us solve 2 or 3 questions on this one. How we proceed. So let us solve this first example under velocity time graph. They are given the motion of y is illustrated on the following graph. To explain, no, is illustrated on the following what? Graph. And illustrated on the following graph, when is incomplete, in the following graph, answer what? Used the graph to explain the motion of the what? Of the curve. So we are asked to what? You are given this graph. You are not expect to what? To explain the motion of car y in the what? In the graph. So the solution, observe that in this, the car y that is travel, but that is being in motion in the graph. So if you look at this graph now, 3 things are involved there. You can observe that what? Here from 0 to this point, the graph is what is accelerate. From this point to this point is what decelerate. The car Y accelerates from rest uniformly with uniform acceleration of what? Of 9 meter per what? Per seconds. But later what? Decelerate with uniform, it is later what? Decelerate uniformly with acceleration of what? 4 meter per what? Per seconds. And it get to this point, it experience a what? A constant velocity. So, because now say what? To solve this now, now what? Can Y start from what? From rest. Why that we start from rest? We not start from the what? From the zero. Assume from the graph. We have the graph like this. And the car start from here. If they now put what? 2 here. This is velocity meter per seconds. Instead of saying what? The car starts from rest. Here, I would say what? The car starts from where? From 2 meter per what? Per seconds. So here now, so if your graph started from the vertical line here, any place in what? In a vertical axis, the body is not start from the what? From rest. But if it start from the what? From this point, it start from the what? From the ori what? From the origin. From rest and accelerate uniformly with uniform acceleration of 9. One acceleration at what? Start from rest. Yeah. And accelerate uniformly because it's a straight line. With uniform acceleration of what? 9 what? Meter per seconds. Uniform acceleration of what? 9 meter per what? Per second square at 5 seconds. So the car started from the what? You want to interpret this graph now. The car starts from what? From zero. And from zero, which is what? At rest. And accelerates uniformly with uniform acceleration of what? 9 meter per seconds at what? 5 seconds. So you take what? 5 seconds for the body to move through uniform acceleration. And get to the what? To this peak value here. What happened again? That's what? Then can Y now what? Decelerate uniformly is what? The what? Decelerate uniformly again. Uniformly with what is acceleration that's used to what? To decelerate. For what? 4 meter per seconds. 4 meter what? Per seconds in another 3 seconds. So for the car to what? To decelerate, this is the region. So when you get to this point, is what? Decelerates uniformly with what? 4 meter per what? Per seconds of deceleration. With how many? What is the time? 3 seconds. How long will be 3 seconds? You subtract what? This 8. You subtract this 5 from what? From 8. You now have 8 minus what? Minus 5. To give us what? 3 what? 3 seconds. So for this car to decelerate uniformly to 4 meter per seconds, what is the time taken there? 8 minus what? 5 minus 8, you have what? 3. And the last one, the third one, It maintains the speed attained for another. It's maintained what at this point now. Yeah, what it maintained it what its speed. Yeah. At this point, now, I said it before that what acceleration equal to the what zero, and the velocity is what is constant here. I said it before now. So to maintain the speed attained for another what what is the time difference between 15 and 8? That will be another 7 what 7 seconds, which is what 15 seconds minus what minus 8 seconds. That is all about the what the interpretation of the what of the graph. If you can know how to what to interpret this graph, you will not have problem with what with the word problem of velocity time what time graph. So let us solve this question. Second question: the motion of the train illustrated on the velocity time graph below. Use the graph to explain the motion of the graph train. This is the graph. And now I have to use to explain the motion of the what of the train. So what solution? You can observe that what the diagram between the two graphs. Here, the car starts from the what from rest, which is zero origin. But here, the train does not start from the what from the origin, start from two. Yeah, Abi. So this simply means what the car does not start from the what from rest. Is already what the car is already moving at speed of what 2 meters per second. So you can now say the what solution the what the train does not start from what from rest. It was already at it was already at speed of 2 meters per second. This one, I said, this y starts from rest because of you have the zero here, but it starts from what 2 here. Simply means what the train is what is already moving at a speed of what 2 meters what per second. That is the first one here. The second one now is what when the car gets into the what from these two now, it will now what accelerate uniformly. It is what accelerate what uniformly with a uniform what speed. It accelerates what uniformly with a uniform what speed to get to the what this 10 meters per what per seconds. From this now, it either accelerates uniformly to move uniformly to a speed of what 10 meters per what per seconds in 3 seconds. So the body of this is now moved uniformly like this, the speed of what 10 meters what per seconds at what at 3 seconds. That's what it accelerates what accelerates uniformly to 10 meters per seconds in 3 seconds. It accelerates what uniformly to 10 what meter per seconds at what 3 what seconds. The next one is what it maintain the speed attain it maintain the what? The speed attained for this speed now at this particular point here. This speed. It will now maintain the speed, which is what 10 meters per second for another. What is the time here? Subtract 11. Take it from 11. The 3 minus 11 we have what? 8. So it will now what? Maintain the what? The speed attained. Maintain this speed here for another what? 8 seconds. Maintain the speed attained for another 8 what? 8 seconds. Which is what? This time 3 minus 11. 11 seconds minus what? 3 what? Seconds. So the last one is what? After this now, it now will then decelerate. It will be what? Then decelerate. Then the what? Decelerate from speed of what? 10 meters per second to the what? To the rest. For the another what? 4 seconds. Now decelerate uniformly from 10 meters per what? Seconds to the rest for another. Subtract 11 from 14, from 15 we have 4 for another 4 what? Seconds, which is what? 15 minus what? 11. That is all about the what? The interpretation of what? Of this. You can see that what? We have acceleration, constant speed, and deceleration. Acceleration, constant speed, deceleration. But because the body started from what? From 2. So what? It does not start from the rest. It was already moving at speed of what? Of this. So that's all about that one. Next thing is what? These two questions is based on interpretation of the graph. So let me now give you solve 2 questions. That is what problem, and then we are going to draw the what? The graph. So let us solve this word problem under velocity time graph. If you observe that the example 1 and example 2, they give us the graph. They are not asked us to what? To interpret the what? The graph. But here they gave us the what? The word problem. You are not expected to what? To draw the graph and calculate some parameters out. So let us solve it now. So I'm going to rub this side. Solution. A motor car accelerates uniformly from rest at 5 meters per second square. At 5 meters what? Per second what? Square. It travels at speed for 4 seconds. It travels at this speed for 4 seconds. Then brake applied. And then come to the rest with uniform retardation in further 8 what? Seconds. Good. They said a car starts from rest. A motor car accelerates uniformly from rest. So if a car accelerates uniformly First of all, we draw what? Our vertical axis, followed by what? Horizontal axis. This is what? Velocity. This is what? Time in seconds. If the car is what? Is accelerates uniformly. From where? From rest. I said this car Y starts from rest. Why? Because it's from what? Zero. This one does not start from the what? From rest. It's already moving at a speed of about 2 meters per second. So here you now say what? Is at rest. Your graph must start from the what? From the zero. At speed of 5 meters per second. That is, at this particular point here, the speed the car used to stand here is what? 5 meters per what? Per seconds. That's the speed here. From rest, here is zero. Then travel at this speed for another 4 seconds. It travel at this speed for another what? 4 seconds. Something is missing here. See here, sorry. 5 seconds in 4 seconds. That's what? And travel at this speed. Yes, so this 5 seconds in what? 5 meters per second in 4 seconds. So accelerate uniformly at rest at 5 seconds. So that 5 seconds means what? Here, trace it down like this. So this place is what? Is forward 4 seconds. That's what? And travel at this speed for another 4 seconds. So it will now maintain the speed, which is 5 meters here for another what? 4 seconds. So if you add 4 seconds plus this 4 seconds, it gives us what? 8 seconds. That's what I did here. That is maintain the speed, attain for another 8 seconds. I say what? 11 seconds. 3 seconds minus what? 11. So so if you add the 4 seconds, that is for another, with this 4, will give us 8. So here we have 8 what? 8 seconds. Here. Then applied the brake applied. When brake is applied to the car, the acceleration will what? Will reduce. Then it come to the what? The brake apply, then come to the what? To the rest with uniform retardation. So when the brake apply, it's come to the rest with uniform retardation. This is uniform retardation. In further 8 what? Seconds. You will now add 8 seconds to another this 8. 8 plus 8, it will give us what? 16. This is what? 16 seconds. So this is the graph you are asked to what? To draw. So completely. The next one is what? You have drawn it. Use your graph to find acceleration. What is acceleration? The acceleration here will be what? You know, I told you before that acceleration from the graph is what? Velocity over what? Over t. What is our velocity here? This side is acceleration now. It should be 5. What is t? Over 4. So the acceleration is what? 5 over what? Over 4. Press your calculator, you get your answer in what? Meter per second square. The next one is what? Speed. Find the retardation. The word retardation is what? Is also changing over what? Over t. So we have 5 over 16 minus 8. We have 8 over 8 is meter per seconds. The last one is C. Total distance covered. This is trapezium. I told that for total distance cover is what is trapezium. Half of what? Let me say this is A, B, C, G, E, F. So it's half of what? A, F plus B, C over what? A over no BB. So you now have what? Half. What is AF? Is 16. BC is 4. DB is what? Is 5. If you add it together, to give is what? 20. Half of what? Of 20. 5. 20 times 5 is 100. We have what? 50 meter as the what? Total distance was covered. So there are some more questions on the velocity time what? Time graph. So the remaining two graphs we are going to check now is what? The graph of the what? Of a body or a ball show from the vertical height, and a graph of what? Of a bouncing ball. After that, we are done with what? Graphical analysis of motion. So let me explain the graph.